Jai Hind to all of you. I am Dr. Ritish Kumar. I am going to give a lecture on the topic of MOS as a capacitance, MOS as a capacitor. So, MOS is a nothing but metal oxide semiconductor. What is a MOSFET? This is a current controlled or I'm asking a question. Is this a current control device or voltage control device? So BJT is a current control device, while the MOS as a voltage control device. So all the things we are going to controlling with the help of voltage in the case of MOS. So why we considering a MOS as a capacitor? So as we know, capacitor has two metallic plates, and between these two metallic conductor we have a dielectric material. So this is a structure of basic capacitor. So if I correlate this capacitor with the help of MOS structure, so we can have a comparison with the help of comparison with capacitor. So here this is a two terminal MOS structure. So MOS similarly as MOS is a kind of n-type MOSFET or p-type MOSFET. Here we are talking about the n-type this is a kind of MOS structure. So in MOS structure we have a p-type substrate here, so that's why we are taking here as a n-type MOSFETs. Generally we have this is substrate layer. We have, you can see, this is substrate layer, this is a metallic contact layer, and this one is the oxide layer, right? This is a oxide layer. So oxide layer is making oxide layer. Here the oxide layer is SiO2 layer. This is silicon dioxide layer. This is a kind of insulating layer. So here you can see in between the metallic and semiconductor layer there is a existing of insulating layer, that is SiO2 layer. So we can correlate this structure with a capacitor. That's why MOS we can say as a capacitor, or MOS has generally some kind of capacitance it has. So here the next one, we need to understand the energy band diagram of for different layer that is existing of metallic, insulating and semiconductor layer. Here we have taken the p-type semiconductor. As we know, the MOS has four terminals, that is gate terminal, and this is a gate, drain, source and substrate terminal. Here we are talking only the two terminals. So that here we have taken the gate terminal and substrate terminal, that is represented by BB, gate terminal and substrate terminal, right? Next we need to understand the energy band diagram for the different layers. So you can see here, this is a metal layer, this is a oxide layer, and this is a semiconductor layer. So here we are talking about, here we have considered, or we have taken the p-type semiconductor, right? Here we have taken the p-type semiconductor. This is a metal, this is an oxide layer. As we know that insulating has a very very large energy band gap, or forbidden gap we can say. So there is no concept of Fermi level in the case of insulating layer material. If I talk about the p-type semiconductor, so Fermi level always lies just above the valence band in the case of p-type semiconductor. If I take n-type semiconductor here, so in n-type semiconductor, the Fermi level lies just below the conduction band, right? So here you can see here, in the case of SiO2 layer, the energy band gap in between conduction band and valence band is very large, right? 8 electron volt. While in the case of p-type semiconductor, here you can see, here I have taken the silicon as a semiconductor, silicon as a p-type semiconductor. So you can see here, energy band gap is 1.1 electron volt because we have considered silicon, and the Fermi level lies just above the valence band, which is representing the p-type semiconductor here, right? So generally, if I take the metallic energy band diagram, so Fermi level, conduction band and valence band Fermi level coincide with each other. So here we have only the Fermi level energy. If this is represented by EFM, right? So this is a electron affinity, and you can see here this E naught is representing the layer of vacuum level energy. The energy of vacuum level is represented by E naught, and this is a Q chi is representing the electron affinity, the carrier affinity. This is Q chi electron affinity. So this is a work function Q phi f. This is a work function of matter Q phi n, right? So this is a representation of energy bands for different layers existing in the capacitor, MOS capacitor, metal, semiconductor and insulating material. So these are the energy band diagram. If I make the for a MOS structure, all the here we have the Fermi level location is different in all the cases. So when you make the structure, if I look in the structure of MOS structure, we have aligned Fermi level. You can see here this is aligned Fermi level. Aligned Fermi level, right? So you can see now, considering that the three components of ideal MOS system are brought into the physical contact, the Fermi level of three material must line up as they form the MOS capacitor. So this is aligned Fermi level. That's why the slope is getting is in the downward direction, right? And there is a bending near the interface of this is a semiconductor and this is the insulating material, right? This is the interface in between semiconductor insulating material, that is SiO2 layer, and there is bending in at the interface layer, right? So next is the MOS system under external bias. Here the Fermi level is aligned under the unbiased condition. Now the MOS system under external bias, we now turn our attention to the electrical behavior of MOS structure under externally applied bias voltage. So assume that substrate voltage is set at VB is equal to 0 and gate voltage be the controlling parameter. That's why we call this is a voltage control device. Depending on the polarity and magnitude of Bg, three different operating regions can be observed for MOS system. So three different regions are accumulation, depletion and inversion. So we need to understand these three regions separately. So first is the MOS structure is in the accumulation region, that is accumulation of charge carrier at the interface of semiconductor and the insulating material. So here in the first point you can see here, if a negative voltage Vg is applied to the gate electrode, the holes in P, because you are applying the negative voltage, holes are attracted towards the gate terminal, or you can say the p-type, in the p-type holes are attracted towards the interface of semiconductor and insulating layer. So the collection of holes, that is majority charge carrier for the p-type semiconductor at the interface of semiconductor and insulating material, is called as accumulation of charge carrier, and this process is known as accumulation process. So this process we need to understand with the help of energy band diagram as well. So in the next slide we will see the energy level band diagram. So here you can see here we have applied the negative voltage at the gate terminal, right? So all the holes, that is majority carriers in the p-type semiconductor, will be attracted towards the gate terminal, and this is a insulating material, that is SiO2 layer, and this is semiconductor layer. So all the holes are collected at the interface of these two layers, and there is a accumulation of charge carrier at this interface. That's why we call this is a accumulation of charge carrier. Now you can see here, you have connected with the negative terminal, so that's why the electric field always be in the upward direction. In the case of if you considering the p type semiconductor, if you take the n type semiconductor, this oxide layer, the electric field within the oxide layer will get in the downwards direction, right? So electric field is oriented towards the gate terminal, as you can see, means electric field within the oxide layer. So this electric field is getting increased the Fermi energy level in the metallic side, in the metallic layer. Initially it has this location. After applying the negative voltage at terminal gate, so we have Fermi level shifted toward the upward direction. That's why this slope is converted to the upward direction, and this one is the downward direction. So all the bending to getting upward direction, as you can see here, previously we have in the downward direction, and right, downward direction. After applying the gate voltage as a negative, we have the bending in the upward direction, as you can see here. So this is a process of accumulation of holes or majority carrier at the interface of insulating material and semiconductor layer by applying the negative voltage at the gate terminal. So now the second MOS structure, second operating region is a depletion region. So now considering the next case, so since the substrate bias is 0, the oxide electric field will be directed towards the substrate in this case, right? The positives now in the depletion case, we need to give some small voltage at the gate terminal. A small voltage, that is some small positive value at the gate terminal. So if you apply the positive voltage, so in the p type, the holes are repelled from the interface, and electrons are getting attracted towards the interface. Holes repel, electron getting attracted due to the apply of positive voltage at the gate terminal, and some holes and electrons are recombined at the interface of this region. That's why there is no electron and holes at the region at the interface of this silicon and semiconductor and oxide layer. So there is no charge carrier present in this region, and only the immobile charge carriers are present. That's why this region is known as depletion region, and this phenomena or this operating in depletion region. So you can see here the electric field direction is oriented towards the downward direction, right, towards the positive to negative terminal. So in the oxide layer, electric field is getting reverse as in the previous case. That's why the energy, so if you look into the energy band diagram for this depletion region, because you are giving the positive voltage and electric field is getting downward direction, so Fermi level is getting shifted towards the downward direction, and bending also has shifted towards the downward direction, as you can have in the previously is in the upward direction, right? But in the case of positive voltage, the Fermi level is getting shifted toward downward, and bending also towards shifted to the downward. If you increase the voltage beyond some certain value, that is called threshold value, up to the threshold voltage, the more number of electrons is getting attracted towards the gate terminal, and a thin layer will be created near the interface of semiconductor and insulating material. As you can see, uh, if you increase or if you give a large value of the gate voltage, more number of electrons is getting attracted towards the gate terminal, and a thin layer is created at the interface of silicon dioxide, that is insulating material, and semiconductor layer. Or in other words, we can say at the interface the minority charge carriers concentration is getting very high, which is creating a thin layer. This layer is known as inversion layer. Why? Because here we are considering the p-type semiconductor, and we have created a layer of electrons, that is minority carrier concentration, which is a inversion of p-type semiconductor, and this layer is known as inversion layer, or also called as a channel in between. This layer is creating a channel in between source to drain, which from this inversion layer the conduction will be happening in between uh, source to drain. So if I talk in respective to the uh, energy band diagram, here you can see, so there is a little bit change in the, if you increase the uh, gate terminal voltage, so as you can have a more shifting in the Fermi level in the downward direction, as we have in the previous case. As you can see, there is shifted in the downward direction in the Fermi level. Again we have a shifted, we have we have Fermi level shifted in the downward direction, and here again you can see at the interface only, interface of SiO2 layer and semiconductor layer. So there is more banding, there is a more banding at this interface, and you can see this intrinsic Fermi level is getting shifted more compared to the previous one, and it is crossing the Fermi level of p-type semiconductor. So by applying the more voltage as gate terminal, this intrinsic Fermi level is getting shifted more down respective to the p-type semiconductor, and at the interface this semiconductor behavior will getting changed from p-type to n-type semiconductor, because this is getting crossed with each other, and due to this crossing this layer is known as inversion layer, right. So and this layer is also known as mean channel in between source to drain, and with the help of this channel we can flow the charge carrier from drain to source, source to drain, and due to which the uh, uh, conduction can created in between, conduction can created in MOS structure. So so in this lecture we have studied about the different operating region of the MOS. The first one is the accumulation, second one is the depletion, and third one is the inversion layer. Also we can understand how we can correlate this MOS three layer structure of MOS as a capacitor, and the things are clear to all of you, I think. Thank you to all of you.